Okay, so we've talked about the simple harmonic motion of some object, some particle, right? Say a mass on a spring, right? But what if that motion were an atom, right? So let's have this be a single atom, and that atom is oscillating up and down in simple harmonic motion. If that atom is connected to another atom, right, in some way, shape, or form, the oscillation of atom 1 can translate to oscillation of atom 2. And there's going to be some lag, right? So atom 1 is going to start moving up. That's going to cause atom 2 to want to start moving up. So atom 2 will start oscillating, but on a little bit of a delay. And atom 3, maybe connected to atom 2, is going to feel the same thing, and so forth. And in this way, the oscillation of one atom connected to other atoms can travel through this material. This is something we call a traveling wave. All right, so a wave is simple harmonic motion that is translated from atom to atom. Let's visualize this. So I have this, some animations, but the animations don't work on the iPad, so we're going to Google these. But this kind of motion, so this is motion of the medium up and down while the wave is going right or left. So let me show you what I'm talking about here. So this is a transverse wave. Again, the atoms are going up and down, but the wave is traveling to the right. All right, this is very much like shaking a slinky, like this. All right, so you hold a slinky. A slinky is a great model for this because all of the atoms are connected by a spring, because it is a spring. Right, so you shake the medium up and down. What's the medium? The medium is just the material that the wave travels through. And almost every wave needs a medium. There's one special wave that doesn't, that you'll talk about in the next course. But again, the medium is just the thing that is waving. All right, so in this case, the medium is the spring. You could do this with a string. And the we'll get back to that. Okay, so this is one kind of wave, and there's another kind of wave. This is a transverse wave, right? Meaning the motion of the medium is transverse; it's perpendicular to the motion of the wave. A longitudinal wave has the motion of the medium is in the same direction as the wave travel. And you really have to visualize this. That's this one. All right, so the particles are moving back and forth, right and left. And the wave is also moving to the right. All right, and it's easy, if you're not looking at the arrows, it's easy to feel like the medium is actually moving to the right, but it's not. The medium remains on average in place, right? The medium is moving, but it's oscillating. This is sometimes called a compression wave, right? It's also a compression. No, I said compression. This is a longitudinal wave because the motion of the medium is along the same axis as the motion of the wave itself. Sound is a compression wave or a longitudinal wave. Earthquakes are also longitudinal waves. All right, so it's not necessary for the air from someone's mouth to reach you, for their voice to reach you, right? The energy is traveling much faster than the air from their mouth is, right? They are labeled here, these two words, compression and rarefaction. You see that there are areas that are dense and areas that are not dense. The dense areas are compressions, that makes sense, and the not dense areas are rarefactions. So again, we'll talk more about sound in the future. We'll watch this video in the future as well. Water waves are actually a combination of transverse and longitudinal waves. That is this animation. Right, and you can see at the surface, the water molecules are making circles, right? Because they're moving both up and down and right and left. And the lower down, they're also making circles, but they're smaller circles. Maybe it's not exactly circular. But you can see here, you can visualize here a peak-to-peak distance, right? So remember, a peak-to-peak distance on a position versus time graph was a period. The peak-to-peak distance on a position versus position graph is a wavelength. All right, so a traveling wave also has a wavelength. All right, and that depends on both the period and the speed of the wave. All right, so the speed of the wave is going to depend on the medium, meaning how connected the particles are, right, and how easy it is to move the medium. So if the medium is really heavy, the wave is going to move slowly. If the particles in the medium are very connected, then the wave is going to move quickly. This is like sound. So sound in air moves at some speed. Sound also travels through solids, right? Like if the sound of my voice hits my desk, it also travels through the desk. It travels through the desk more quickly because the desk is a solid, right? The atoms are connected much more than the air molecules. In ideal gas, the air molecules aren't connected at all. So sound wouldn't travel through an ideal gas. Luckily, we don't live in an ideal world. There's a wave so important that we call it the wave. Let's see if it loads. Let's try one more time.
You are looking at...
No.
For the words we've all been waiting.
That's not what I wanted.
You are looking at a new world record for the wave.
Fine.
Attempt, can they do it? 168,000. They are here from the Guinness Book of World Records to certify the record if they can make it all the way around. Yes, folks, just another sellout crowd here at the world's fastest half mile in Bristol, Tennessee.
Looks like it's getting off turn 2 pretty good. Building a little momentum down the backstretch here.
Got to get it to turn 3. We're going to have a record if they can make it all the way around. They would break the record by some 50,000 fans. And they have...
Okay, that's enough of that. So the point is, that wave is also a wave. It's a traveling wave, right? The medium is people, and when the person next to you raises their hands, you raise your hands, and then the person next to you on the other side raises their hands. That's oscillation of the medium, right? So each person raises their hands and puts them down, but they don't travel, right? The thing that's traveling is energy, right? It's this disturbance of the medium that's traveling. Can we describe this mathematically? Absolutely. Absolutely. but it requires both time and position, right? Because the wave is changing in time, and it's traveling, so it's moving positions. So here we have several plots of position versus position at different times. All right, several plots of position versus position at different times. So the top plot there shows an arrow, right? The arrow V to the right is the direction of motion of this wave, and after a quarter period, the wave moves a little bit. After a half period, the wave moves a little further, and 3/4 moves a little further, and in a full period, it moves far enough that the peak behind the initial peak is where the initial peak was. All right, so that's a special distance called the wavelength. All right, so you could define wavelength as the distance the wave travels in one period. Right, so you can determine period by looking at the motion of a single particle in this wave, and you can determine wavelength by looking at the aggregate motion of all of these waves over a period. And you can see we describe position as a function of time, just as we did for simple harmonic motion, and we describe position as a function of position also by a cosine. All right, and you can put these two together to describe the motion as a function of position and time together. And you have a choice. You can use sine or cosine. We're going to use cosine, but it doesn't really matter. They're just offset by a half cycle or quarter cycle. All right. This animation I'm not going to worry too much about. The sign between x and t defines which direction the wave is going. The negative sign means it's going to the right, which is a little counterintuitive. So we have these two properties, right? This amplitude, this wavelength, and I guess we also have period, so that's 3 properties. Again, wavelength there is that Greek letter lambda. Let's talk about wave speed. Wave speed is distance traveled divided by the time it took to travel that distance, and we just said that there's a special distance that is the wavelength, which is the distance traveled in exactly the period. So if you divide those two, wavelength divided by period, you get a speed. That is the speed of the wave. You can also recall that period is 1 over frequency, so you could also write this as lambda times f. This is true for any wave, that the wave speed is the wavelength times the frequency. And the wavelength is determined by the medium. I think I already said that, but you can change the wavelength of a traveling wave by changing the driving frequency, right? This would be like if we go back to this picture, right? You decide how quickly to move your hand up and down, right? That determines a frequency. And if you shake your hand faster, the peaks are going to be closer together because you're sending a peak out with less distance between the peak you're sending out and the peak you already sent out, right? So that's going to be a shorter wavelength, but the wave speed didn't change. All right, wave speed is a function of medium, not a function of the frequency or wavelength on the wave. Okay. Yeah, I think that's good for this. So let's go talk about, let me write that equation again. So we had y of x and t is an amplitude times cosine of, we had 2 pi x over lambda minus or plus, depending on the direction of travel, 2 pi t over period. All right, and I want to remind you, 2 pi over t, that's the same as omega, right? So you could have written this as omega t. And this 2 pi over lambda, we also define another variable, 2 pi over lambda. We define a variable k. This is wave number. It has units of radians per meter. Alright, it's just another way. So you could have written this as kx minus omega t. Alright, but then from this equation, you could grab this information, right? You could see what the wavelength is from this, and see what the period is from this. Let's do a quick example. In the lecture handout, here's the description of that. Nope. Yep. This has a sign, but again, it doesn't matter. There's your kx. The k equals 2 pi over lambda. Here's your omega. And the wave speed description. Again, lambda over t, lambda times frequency, and it looks like you can also do omega over k. Let's do this example. So example 6 says a traveling wave has a displacement given by this equation. Identify a bunch of stuff about it. Okay, so what's the period of this motion? Well, we're just going to read it, remembering that the equation for this is a cosine kx minus omega t. So whatever's sitting in front of t must be omega. Right? So let's change colors here. So this is omega. This must be the wave number k, and whatever's sitting in front of cosine must be the amplitude. By the way, we must be describing a transverse wave here because the wave motion is in the x direction, kx minus omega t, but the medium motion is in the y direction. That's y of x and t equals, right? If this were a compression wave, I guess we could say x of x and t equals. But sometimes instead of that, we'll do a pressure, right, or a displacement from equilibrium pressure. That would be like for sound, right, since sound is a pressure wave or a compression wave. Okay, so what's the period of this wave? Well, we'll stay with blue. So we just said omega equals 4 pi radians per second. That doesn't look much like a pi. Now I want some pi. And that equals 2 pi over the period. So I can solve for period then. Period is 2 pi divided by 4 pi. 4 pi radians per second. And what I get then is the pi's go away, I get a half of a second. Right? And what is the wavelength? Well, wavelength, remember wave number is 2 pi. Just reading it directly off of the equation. Sorry, radians per centimeter. That's not an SI unit, but that's okay. We'll just carry the unit with us. So wave number is 2 pi over the wavelength, which means wavelength here is 2 pi divided by 2 pi. So that's going to be 1. But what are the units? Well, that's radians per centimeter. So that's 1 centimeter. Maybe 1.0, but who's counting? Wave speed. How do we get wave speed? Well, we had a couple equations for this, right? We said wave speed is lambda times a frequency. It's also lambda divided by a period, and we have those two numbers. We just found those two numbers. So lambda is 1 centimeter, and the period is half of a second, so it looks like this must be 2 centimeters per second. Okay. And again, if we change the wavelength of this wave, it would change the period, but not the wave speed, as long as we're not changing the medium. What direction is this traveling? Well, remember I said the negative sign means we're traveling to the right. And a positive sign would mean we're going to the left. So this is right traveling. And then the last thing here, let's do this quickly. Sketch this wave and then sketch it again at an 1/8 of a second. So let me do this. Let's decide a time scale here. 1, 2, 3. I want this to be about half a centimeter. What's that, 4 points? This will be 1 centimeter. This will be 1.5. This will be 2. This will be 2.5. Okay, and let's let the amplitude be like 3 tick marks up and 3 tick marks down. So this is minus 2 centimeters, and this is positive 2. That's the amplitude. Yeah, 2 centimeters is the amplitude. Right? Where am I getting that? That's this right here. Right? The amplitude is 2 centimeters. Okay. And we want to plot it at t equals 0. So at t equals 0, y of x and t is a cosine kx minus omega t. Well, omega t is 0, right? So this bit goes away. So it's just kx. So it's just cosine, and cosine at position 0 is cosine of 0 is 1, right? So this should start here. So I'm going to start up there, and it should repeat itself every wavelength in position, and the wavelength is 2 centimeters? No, the wavelength is 1 centimeter. So it should come back to this point up here, which means halfway through it's going to be here, and then halfway between those it's going to be there. And then at 2 centimeters it's going to repeat itself again. And it's going to come back to another half cycle. Okay, so this is what it should look like. Okay, that's pretty good. Again, the way I drew this was I put dots where I knew the peaks were going to be, and then I put dots where I knew the middles of those were going to be. How did I know where the peaks were going to be? Again, I knew it was starting here, and I knew the wavelength was 1 centimeter, so it had to come back to that point after 1 centimeter. Alright, and so it had to come back to that point again after 1 centimeter. So that's the top points. And between the top points, exactly between the top points, is the very bottom point, right? So I knew halfway between 0 and 1, it was going to be down here. And then halfway between a top point and a bottom point, right, a peak and a valley, it was going to cross 0. And those points helped me plot this. Let me get rid of a bunch of this. Maybe just that much. Okay, so let's plot this 1/8 of a cycle later. So a full cycle, it will have traveled the full length here. In a half cycle, so this would have been a full cycle. A half cycle would be here. Oh, it's an 1/8 of a second, not an 1/8 of a cycle. Let's see, an 1/8 of a second is a quarter cycle, right? Since a half second is a full cycle. Does that make sense? It travels here. This is the distance. This is the distance it travels in one cycle, right? So that's a half second, which means half of this is a quarter second, which means half of that is an 1/8 of a second. So in an 1/8 of a second, this peak will have moved to here. All right, so every point on this is going to move 2 tick marks to the right. It's going to move Yeah, 2 tick marks to the right. Another way to get that is to say v equals lambda over t. I mean, basically here, v equals something we know. V equals 2 centimeters per second, I think. Yeah, 2 centimeters per second. So I could ask, how far does that travel in 1/8 of a second? Well, I'm going to get, nope, almost there, 1/8 of a second. Well, distance equals speed times time. So it's 2 centimeters per second times 1/8 of a second. That's 2/8 of a centimeter, which is 1/4 or 0.25, right? So if this is a half, then 0.25 is right here. Okay, so every point on this is going to move that much further to the right. We'll have it end right there. Okay, and it's going to cross through the middle here. I think that's right. Okay, yeah, let's try that. And this is going to start then at the bottom. Or sorry, at the x equals 0. Okay, that's pretty good. So again, it traveled a 1/4 of a centimeter in that time, and we calculated that just by using the wave speed, right? Speed is distance over time. It has the same wave form, right? It's still a sine or a cosine. In this case, it's a cosine that's just shifted to the right, and that's because now omega t is not 0. Right now, we've added a non-zero t, so x had to get bigger so that the argument of this moves to the right. Okay, so that's traveling waves.